I'd like to look at a number of sort of discrete frequency responses that come off of discrete impulse responses. And it's kind of good to look at a couple of them and look at just how some of these things compare with each other when you actually put these things together. Now remember that for frequency response, right? You're talking about an H of n is typically your impulse response. That's the response that you would get at the output if you put an input into it. We can go directly from H of n to H of z. There's a direct transform approach to go between those two. And then to get to frequency response, you usually take z to the minus 1 is equal to e to the minus j omega hat. Omega hat being in the sample discrete space. All right. So now, how to look at this? Well, I want to look at a couple of different cases. I'm going to actually look at two cases that are IR type of filters and two that are FIR filters, and just kind of notice the different properties we see out of these two filters. Now, the first one here is going to be a very basic filter for an IR step response, where this particular one, and this is going to be 4, 3, 1, and 2, just sort of different kind of ordering I like to use in different cases here. But this particular one is 0.6 times n, 0.6 n u of n. So basically it means that the very first part of the impulse response is a 1, and then all the way down. So it's good to just kind of visualize what these look like as well as look at the analytic forms. And so if you were to take this and say, well, what does its frequency response look like? Well, you would immediately say, here's my h of z. That becomes h of omega hat, and I could immediately plug that in as a j omega hat there, and you're like, great, and go plot it. And you're thinking, well, the first thing you do is like, okay, let me go find MATLAB. That might be easier, or some other happy coding approach. You take that structure, that would work. You might take but one of the other things is it's good to kind of get a sense what's going to happen in the rest of the structure. And one of the interesting parts is the IR types of structures also have a correlate to some of the continuous time types of operations. So you might say, typically when omega hat is small, significantly less than pi, like 1 or less, you typically get something that looks a lot like maybe a continuous time form. So that might give me an interesting idea. What happens if I were to linearize this term here? What would I see? Well, what I would get is effectively a response that's 2.5 times 1 over 1 j 1 plus 5 omega hat. Kind of interesting. So it says that the peak is about 2.5, which in fact is what you get. This definitely gives you the form of a low-pass structure, because as omega hat gets large, what happens? The number in the denominator gets small, and as a result, or it gets bigger, so the whole overall term gets smaller, so I'm getting less. So I would expect that's what I'm going to see here. Starts from a peak and then falls out. Okay, that's cool, right? And to just kind of get a relative sense, at pi over 4, the number I'm going to get is 1.4, because it'll be an interesting number to kind of keep around just so we can watch what's going on here. When I look at the second case, which is very similar, now it's 0.5, but it's now I've delayed it by 2. Now the delay in the magnitude of the frequency response would basically have no effect. It would certainly impact the phase, and so there's a phase shift that would come along with this particular system. But in terms of magnitude, I get an h of z looks like that, the frequency response, and then I also can look at the linearized cases. Linearize the one exponential near omega small. I didn't worry about it on the numerator because I knew that's just a delay and it's going away, so I'm not going to worry about that first. And what happens is the peak is about 2, and then it also drops. Interestingly enough, when you calculate it at pi over 4, you get almost the same value as you did in the first one. So kind of an interesting thing to notice as you look at these problems. So, but IR filters almost always will have the impulse responses that drop. You'll almost always have responses when you look at this that start off with some peak that'll often drop if it's a low pass type response. If it's kind of a band pass or high pass or other things, you'll see some other characteristics, but you get a very smooth behavior in sort of the linear frequency response. Now, if we were to take the log of it, you'd see a little bit different perspective, but we're going to kind of just keep it in linear space for omega and transfer function here. Now, you get two other FIR responses. The first one of those two is a classic boxcar response. And you have 4 of them, and so this is your impulse responses for these 4 of them in a row, all the same magnitude. Interestingly enough, we kind of would know that what its z transform is, it's a 1 minus z to the minus 4 or 1 minus z to minus 1. It also could be a sum of the 4 z's, being 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. That all works, right? But this also gives me a different form of it, which also is a very familiar form. Probably many of you listening may have seen these kinds of forms, which then gives me a very familiar form of the frequency response, which is quite useful because in the end I can look at this and go, well, what kind of number would I see? What kind of number would I see here? Well, the peak of this is going to be 4, and so that gives me a 4 here, which is not surprising. There are 4 of these. Probably expect 4. And then it rolls off, and I actually get these zeros, right? In fact, I get 3 zeros here, one at minus pi over 2, one at pi over 2, and one at pi. There's not another one at pi, minus pi because it's the same point. It has a periodicity of 2 pi, so it's always the same thing. It's 3, you get 3 zeros out of this because you actually get 4 things out of the numerator, but you get subtract 1 from the one in the denominator. So you go, that's great. That gives me a particularly good case. At pi over 4, it's about 2.62, so that's, gives you a rough kind of perspective where you're sitting there. And then you say, well, okay, now what would happen if I take this boxcar and make it a slightly different form? Just because it's kind of fun to do. And go, well, imagine instead of being all ones, it's 1 to 0.7, 0.5, and 0.25. Well, obviously the peak is going to get smaller because the magnitudes are smaller. But I notice a couple other things that happen out of this. It becomes a peak here, but I never quite get the zeros. This is a function that's never quite going to 0. In fact, if you look at it closely, this actually has a form that almost feels like an IIR type response. Take a close, if you look at this, you could almost imagine this being something like being a value times 0.75, 0.5, and watching it iterate. It's very close to that. Now it would kind of curl over a little bit more, but it has a little bit more of a IR type response because it tends to look like this, but it's not quite. So you kind of get, approaches a 0, but not really, and then stops. And so you get some very interesting frequency responses, and it's neat to kind of look at what you get in the discrete space of the different kinds of properties. There's plenty to talk about and plenty of discussions here, but it's kind of interesting to see what kind of properties you get out of these systems.